Hello, and best wishes and greetings from Germany. First of all, I would like to introduce myself. My name is Dominik Aufderheide, and I'm Professor for Industrial Metrology here at the Southwestern University of Applied Sciences in Soest. And it's a great honor for me today to present a research topic which we conducted together with our industrial partner, the Matteo Group, which is an engineering and construction company for bulk material handling equipment, also here in Germany. And of course, I'm really happy to be able to present today here at the conference organized by our partner university, ESGU. And I would like to speak about a hardware-in-the-loop approach for factory acceptance testing of gravimetric dosing systems. And during the next 10 minutes, I would like to give you, first of all, a general introduction into the topic. And of course, I will mainly speak about the machine which we used for this research. Based on this, I would like to introduce you in the sophisticated system architecture which we are following for our hardware-in-the-loop approach for factory acceptance testing, which also consists of a hardware-in-the-loop simulation model, which I would like to also briefly describe before I will show you the results we were able to achieve and conclude the whole talk. So starting with the introduction, I would like to give you an overview about the machine itself. This is the ODM weight tube, which is an award-winning and patented system for gravimetric dosing of bulk materials, which means that this is the machine responsible in your overall configuration of machines, which actually is able to deliver a 30 defined set point of mass flow, which means, for example, that you can define, I would like to have from this kind of bulk material 10 tons per hour, 20 tons per hour, whatever you want to have. And this machine is responsible to actually precisely dose this kind of material into your process, for example, into your combustion process or dosing process. So the system itself consists of a buffer, which actually receives the bulk material from all pre-feeding conveyors. The buffer also contains an agitator, which is actually responsible in order to generate a homogeneous fill level of the buffer. The material is then discharged from the buffer by means of a dosing section of the screw. The material is then further conveyed to a second section of the screw, which is called the tube section. This section is actually decoupled from the fixed frame of the machine in order to be able to use it as a measuring section. Since it is placed on load cells and it is not coupled with the fixed frame of the machine, we are able to actually measure the material weight in this particular part of the machine. You can also see that the system is able to calibrate itself by means of the buffer weight for which we use actually second set of load cells. This is actually one of the highest selling machines of the Matteo company, and therefore the machine is now available in complete different varieties and model based on the bulk material, based on the application which you actually follow. The problem is that there is a great variety of designs and architectures. Each control system needs to follow these kind of unique designs, and it is always designed and tailor-made for one specific machine and based on the client design guidelines. Therefore, the company had the big problem that it can only achieve the high quality they want to have if they do excessive factory acceptance testing of the control system. Usually, this was actually done in a manual way, but this has some disadvantages since it is quite difficult to execute, because what they need to do in order to test the cabinet is that they need to connect manually the cabinet with the real machine in the premises of the Matteo, which is quite time consuming, and you require, of course, very experienced staff in order to do so. Furthermore, the whole testing is always subject to human error, because each and every individual tester will do the tests in a not exact same way, and of course, if they have a bad day, we will have bad results of the factory acceptance test. Therefore, the company contacted us as a university if we could help in order to develop an automatic factory acceptance test program. This program shall be able to actually work for all possible machine designs and parameters. It shall only require minimum interaction of humans in order to reduce the errors of the testing, and it shall consist of an automatic reporting and documentation process. Secondly, I would like to speak about the system architecture we followed in order to realize such an automatic factory acceptance test system. The system architecture is therefore based on the hardware-in-the-loop approach. This means that, first of all, we have the hardware under test, so the system we want to actually evaluate. This is, in most cases, the real control cabinet, which consists of the typical components of an automation system, like a PLC, frequency drives, and all the switch gears, like contactors, motor protection switches, relays, whatever it will be. By means of a certain interface, based on certain inputs and outputs, we now connect the cabinet not to a real machine, but to our computer in simulation. This contains the hardware-in-the-loop simulator of a machine model and a real-time simulation, which is able to actually react in the same way as the real system would do based on the outputs received from the control cabinet, and it is able to even simulate the complete behavior of all inputs to the control cabinet. Based on the system behavior, a verification engine is actually able to generate an automatic report whether the system is actually following all the requirements. Finally, we have also the user, but his interaction is only very, very limited, since he's only there for supervision of the process execution and in order to see whether there are some bigger errors so that the test cannot be finished. I would like to speak a little bit more about the machine model as a core part of the hardware-in-the-loop simulator. Therefore, we will have a short look on the hardware-in-the-loop simulation model. The hardware-in-the-loop simulation model mainly consists of a complete mathematical physical description of the complete machine, which means that we abstracted the real machine in terms of certain parameters, mainly geometric properties based on the different models available from the company, on the motor behavior, on the screw design, and all the parameters we need in order to describe the process in a physical, mathematical way. So, for example, we find actual equations for simulating the mass flow, the buffer fill level, the weights, and all the different process aspects which we need in order to evaluate our control. Therefore, we were able then to connect the simulated plant by the certain interfaces with all the components in our real cabinet. So that means that at this point we were able to actually completely neglect the real machine, but we can rather connect the simulated machine to the control panel. For the verification engine, it is possible that the user is selecting which kind of tests shall be executed automatically during the factory acceptance system. Each of these individual tests can be set and manipulated by parameters. The system itself performs these tests automatically and generates certain reports by using, for example, measurements from the process. And then the supervisor can see whether certain tests are passed or failed and can actually generate the report. Finally, I would like to speak about some results we were able to achieve. In order to do so, what we have done is that we have a comparison between the actual simulated system with all the control elements and the hardware under test, the real system. And then we can do a verification whether the real system just behaves as the simulated one. Here are some examples of the results. First, we validated whether the system is actually behaving exactly as a real system would do. As you can see here, we performed a set of real data runs, which are shown here in blue, and compared it with the simulated data shown here in orange. In order to verify in a numerical way the actual differences between these runs, we calculated the correlation between the real data runs and the simulated data. It was found that even in the worst case, we have a correlation coefficient of 0.92, where 1 would be the optimal solution. So we are quite happy that the system for different typical states, like filling of the tube, emptying of the tube, or emptying of the hopper, would react just as the real system. Furthermore, of course, we want to see whether we have a step response or ramp response as we would see in the real world. So here you can see a mass flow step response we actually defined as a set point. And this is how the system is able to react. You see in blue that the system just reacts as a set point, so the controller is really able to work. And in blue, you see the actual screw speed, which was simulated. On the right-hand side, you are able to see the ramp response in the same way. Let's jump to the conclusion. What we found is that our hardware-in-the-loop testing is actually successful, and it was a good proof of concept for this specific machine. It is now, of course, in discussion with the company to extend this approach to other machines, since we also found out that we are very successful and the model works just as good as the real system for testing purposes. So thank you very much for your attention, and of course, I would like to answer all of your questions if there are some. Thank you for your attention. It was a great pleasure to be able to present my work. Thank you very much.